Okay, now here we want to look at what would be called a library of functions. What are some different function types that we really want to be able to recognize? So some of them are going to seem familiar. We would like to recognize lines, and we can recognize lines. We would like to recognize parabolas. We would like to recognize rational functions. We'd like to recognize radical functions, absolute value, and we would like to recognize a greatest integer function. So some of these should be pretty familiar already. If we look at a line, simple, right? Look at a parabola, just as simple. Look at a rational function. That's going to look like this. It's going to be a little bit more involved. I'm going to put down a couple of asymptotes here, like so. And then we would draw in the rational function like this. A radical function you might recognize like that. The absolute value function looks like a V. And the greatest integer function is most likely new to you, and that looks like this. Looks like a staircase. And in fact, it is also called a step function. I think there's one other that I'll add on here. I'll change the page. And one other that I would add on here would be a cubic function. And these are just some immediate functions that we're interested in. We're going to add other types of functions over the course of the semester. This is a cubic function. I'll do it in red like I did the others. All right, so there's a cubic function. Now the idea is that once I know the family of functions, I want to be able to recognize it whenever I see it in an equation and have an idea about what shape to expect. So if I were, of course, when I see an equation like this, say y equals 3x minus 2, I know that's a line. And then I would also want to know that if there's some sort of variation on that, like I've got y equals negative 1/2, I've got x plus 1 minus 1, something like that. And there's a little bit more going on there. It's not in slope-intercept form, but I know that if I were to simplify this and rearrange it, that I could get it to look like the 3x minus 2 function. Likewise, with the parabola, we have this obvious here, y equals x squared. Obviously parabola, maybe even obvious if I add something to it. Y equals x squared plus 1, obviously parabola. And I also want to recognize that if there's a little bit more going on here, like say I've got x minus 2 squared, so the x squared isn't explicit maybe. Maybe it's hidden in there a little bit. So here I've got the x squared, right? So I know that's a parabola. Now this one, I don't have the x squared, but I know that if I expanded this and applied this 2 here, when I expanded it, I'm going to end up with x squared. So it's going to be a parabola. And so I'm recognizing the family of functions that are parabolas. Rational functions, maybe you're not as familiar with, but that's going to involve something with 1 over x. That's going to be the rational function. Radical function, of course, is going to involve a radical x. Absolute value function, absolute value of x. Let me talk briefly about that. This absolute value function, see, we can have this variation on it, right? And we understand that above. So if I have y equals, say, negative 1/2 absolute value of x plus 1, I recognize, okay, this is that basic family of functions that is the absolute value function. It's going to look like a v. Now there can be variation. There could be other types of absolute value functions. For instance, if I went like this, I could have an absolute value function, and I could have a quadratic in there. So I went like that. Okay, that's not going to be v-shaped. So the specific type of absolute value function that is in our library of functions that we're talking about. So we're not talking about these other potential variations. But we have an idea. When we look at the function, we want to know, do we have an idea about what is this going to look like? All right, and then we have the step function. Okay, the greatest integer function down here. That's a new notation that you haven't seen. So looking down here at the bottom of the page, this is what the greatest integer function notation looks like. It looks like a bracket with an extra line there. And that's the greatest integer function. So I'd like to talk a couple of minutes about that maybe, so you can see what that looks like. Of course, here's that cubic function. That's y equals x cubed. And again, it could be buried in there, right? So if I had x minus 3 cubed, I'd know that if I expanded that, I'd have x cubed, and it would be a cubic function. So let's take a look at this greatest integer function that you're being introduced to. The greatest integer function, so I've got y equals, and I'll just take the basic one since you've never seen it before. And what this notation means is, it's what's the greatest integer? The greatest integer that is less than or equal to x. That's how we evaluate it. So you might take a moment and think about that. If you don't understand what that's saying, we'll look at the example. So I'm going to take and do a table of values here and just look at a few values. All right, so let's take 0. That's always a good place to begin, right? So I would have y of 0 is equal, and then I'd plug in a 0 for x. And then to evaluate the output here, so I'm saying, what's the output? What is my output for y when I read this, when I'm reading this notation? And again, the way to read it, I've indicated above, is that this is asking, what's the greatest integer less than or equal to x? So I would say, what's the greatest integer that is less than or equal to 0? Well, that's easy, right? Because 0 is equal to 0. So the greatest integer that is less than or equal to 0 is 0. So that's going to be the output here. Now, in order to have a good appreciation for this, we're going to have to look at some fractions. So if I let's take 1/2. And then I plug in the 1/2. And evaluating that, let's ask ourselves that question. What's the greatest integer that is less than or equal to 1/2? The greatest integer that is less than or equal to 1/2. So maybe you think about that for a moment and you say, oh, that's a 0 also. I'll just continue here with another one. So 3/4. What's the greatest integer that's less than or equal to 3/4? Again, 0. And I'm not going to flip over until I get to 1. So all of these fractions between 0 and 1 are going to have an output of 0. And then finally, when I get to 1 and I plug in a 1 for x, that's going to be, what's the greatest integer that is less than or equal to 1? And that will be 1. And then I run through the whole cycle again, and I could have 1.1, I could have 1.5, and I could have any 1 point anything in here. And all of these, the greatest integer that is less than or equal to this these numbers is going to be 1, 1, 1. I'm going to keep getting an output of 1. So when I graph this, if we can think about the graph of this, if I go 1, a scale of 1 on the x-axis and a scale of 1 on the y-axis, and then I plot the points 0, 0, 1/2, 0, 3/4, 0. So you see, if you look at my axis down there, and I'm plotting the points in red, so they're all going to be red here. All going to be red up until I get to 1. Then I'm not going to hit 1. At 1, so look at the table that I just circled there. At 1, I'm going to jump up to 1. So I'm up here. And then I'm going to be there until I get to 2. And then I'm going to jump up to 2. And then I'll be on 2 until I get to 3. And then I'll jump up to 3. And then to really get the detail correct, when I get, in order to indicate that I jump at 1, I'm going to put this open circle here. Open, and then I jump up to 2. And then open, and then I jump up to 3. Open, and then I would jump up to 4. Open, and so on. And that's a step function, which maybe you're seeing for the first time. So we'll add that to our family of functions and work with it a little bit, and then you'll probably see that more if you go into calculus. Also shows up in engineering as well, electrical engineering, etc. Okay, so that's all for today.